Hi, welcome to my digital sampling lab. So, the objective of this experiment was to familiarize ourselves with digital data acquisition of time-varying signals. We also could explore key concepts like frequency analysis and sampling theory. Some of the key phenomena that we studied were Fourier series and Fourier transforms, power spectra, filtering, Nyquist limits, and aliasing. The importance of this experiment is that real-world signals are often composed in multiple frequencies, and Fourier transforms let us decompose signals into their components. So the approach for this lab was initially using a whole LabJack T4 DAC and then also the GTAE Symbol DAC software. That is what is shown on the top right and what was used for almost all measurements. In the software, we can pick a sampling rate, record length, filter, and in the time history, we can observe the waveform shape and other such components. In the power spectrum, the bottom graph, that is a frequency response, and we can use that to analyze frequency power and can record VRMS and peak frequency. Now for the results of the general lab. So these were the 11 tracks and their measurements that were supplied to us. For track 1, I recorded a low frequency sine wave at 100 Hz. For track 2, I observed a medium/high frequency sine wave at 1000 Hz. For track 3, there was a triangle with a main frequency at 1000 Hz with harmonics at 3000, 5000, and other odd thousands. Track 4 was a square wave, which I thought had a bit of noise, which had a peak frequency at 1000 and 2000 Hz with harmonics every 1000 thereon. Track 5 was a highest pure sine wave at 3000 Hz. Track 6 was a sawtooth function with peak frequency of 1000 and 2000 Hz and other harmonics in the thousands as well. Track 7 and 8 were noisy sine waves, both at 1000 Hz, and we will talk more about those later. Track 9 was a sum of 3 sine waves at 100, 1000, and 10,000 Hz. Track 10 was the sine times a sine wave, where we had 2 distinct peaks at 900 and 1100 Hz. And then track 11 was a sine wave where frequencies ranged between 0 and 1150. I then went into recording observations about record duration and related parameters, and I demonstrated that the record duration is inversely related to the frequency resolution. This led to observing the relationship record duration is equal to record length over the sampling rate. Then we went on to the Nyquist investigation, where we could see that only at about 2 times the highest frequency in the signal, which was 10,000 Hz, we get almost a clean signal, where we can see at 20,000 Hz sampling rate, we can get a perfect reading for frequency 1, frequency 2, and almost perfect for frequency 3. Only at an even higher sampling rate, 25,000 Hz, we were able to get a perfect reading for all of them. Then I talked about and discovered stuff about the signal-to-noise ratio. When we look at track 7, we see 150 about, and for track 8, about a 33 signal-to-noise ratio. This would indicate that there is more noise per signal in track 8. This aligns with track 8 being noisier in the initial readings. In the filter investigation, there was a lot of DC noise, so the peak power of the provider frequency, 10 kHz, was already at negative 20 decibels when measured. I decided to cut and filter out noise by a significant amount, which meant that I was going to cut it out until it was at 0.707 times what it initially was, which is a significant change in the electronic signal world. I decreased the passband range until the low pass filter was at 9300 Hz, where the 10 kHz signal was decreased to negative 23 decibels VRMS, a 3 decibel decrease. For my custom experiment, I wanted to talk about amplitude versus distance. It is blatantly obvious fact that sounds get quieter the further out you are away from them. I wanted to finally prove to myself what the relationship we've been experiencing our whole lives really is. My question is, how does magnitude and/or frequency change as a function of distance? My experiment's goals were to create a relationship between signal amplitude and distance, substantiated by evidence. The procedure was to follow the standard microphone accuracy measurements, then on a piece of paper or table or something, measure out tick marks with a ruler, and then set up the microphone, set the speaker volume to 100%, and play 4 different frequencies at 4 different distances and record how they vary in amplitude and frequency. This is my experimental setup. You can see the LabJack in the background with a microphone next to the end of the paper with measurements on the side, and then my phone in place for where the speaker would be. These are the results from the experiment. We can clearly see that frequency did not change. However, we can see the final final measurement versus initial is about 14 to 20%, except for 5000 Hz, which I will talk about later. So, for the results, I did observe a significant amplitude decrease over the same distance across multiple frequencies. Frequency did not decrease at all, which aligns with my thinking before the experiment. So this is why I call the experiment a success. I successfully demonstrated a consistent relationship between amplitude and distance. There was about an 80% amplitude decrease over a 5x distance increase. I believe there was some complication of the 5000 Hz sample due to significantly higher retention of the amplitude of the second and third distances. I believe this is possibly to be some sort of resonant frequency of the component of the microphone or other interfering parameter. So I successfully characterized various waveforms, including triangle, square, sinus, and more, and this links the time domain of observation to the corresponding power spectral features. I observed the role of Nyquist limits in avoiding aliasing by requiring at least a 2x sampling rate of the highest signal frequency. I demonstrated that the record duration is inversely related to the frequency resolution that led to observing the relationship RD equals RL over SR. I observed noise and its impact on the usability of data, especially at lower signal power amplitudes. I applied filters to attenuate noise in a 10 kHz signal, reducing power to negative 23 dB VRMS, and demonstrated how to clean signals while retaining essential information. I confirmed the relationship between amplitude and distance, observing about an 80% decrease in amplitude with a 5x increase in distance. I believe this almost aligns with the inverse square law, which is how wave power decreases. Although successful, there was some potential interference with potential resonance in the setup at 5 kHz. Thank you.